forget to like and subscribe this channel.
Assalamualaikum. Hi everyone, it's me again. I'm Madam Nurul Hidayah binti Kamadin and I'm going to teach you chapter 5. In this chapter, you are going to learn the beauty of gas, liquid and solid. Okay, let's start. For chapter 5, the topic is states of matter. There are 4 subtopics in this chapter, which is gas, liquids, solids and phase diagram. Now we are going to study 5.1, which is gas. For the learning outcome for this video, you should be able to explain the basic assumption of kinetic molecular theory of gases for an ideal gas. There are 3 states of matter, which is solid, liquid and gas. So we can clearly see the main difference between each state is the arrangement of particles. Now let's look at properties of gas. There are 6 properties of gas, which is shape, volume, compressibility, density, flow and miscibility. So today we have a bottle of chlorine gas. For the first one, which is shape, the shape of gas follow the shape of container, and the volume of gas will equal to the volume of container. Next, look at the compressibility. Is it easily compressed or hard to compress? So gas can be easily compressed, so it is highly compressible. Now let's look at density of gas. So we all know that gas has very low density. Next, let's look at flow. So we all know that gas can flow more freely. And the last one, gas is easily miscible among each other when they are put in the same container. Now let's look at kinetic molecular theory of gases. So, kinetic molecular theory is a model to explain the behavior of gaseous particles and is based on extensive observation of the behavior of gases. If the gas follow all the postulates of the kinetic molecular theory, then the gas is called ideal gas. There are 4 basic assumptions in kinetic molecular theory. The first one, volume of gas molecules are negligible compared to the volume of its container, meaning that the volume of gas is equal to the volume of container. Next, the intermolecular forces between gas molecules are negligible. It means that we can ignore the intermolecular force between all gas molecules. The next one, collision between gas molecules are perfectly elastic, meaning that when gas molecules collide among each other, there are no energy loss between them. And the last one, the average kinetic energy of molecule is proportional to the absolute temperature. It means that when we increase the temperature of gas, the kinetic energy of gas particle will also increase. Let's look at the first one. So the volume of gas is equal to the volume of container. Let's say we have 1 liter of gas. So let's say we have 1 liter of container. So it means that we also have 1 liter of gas. The next one, the intermolecular force. So for ideal gas, we can ignore that for ideal gas, we can assume that the intermolecular force between each gas particle is negligible. The next one, elastic collision, meaning that when gas molecules collide among each other, there is no heat loss during the collision. The next one, when temperature increases, the kinetic energy of gas particle will also increase. There are 4 parameters that we can use to describe gas, which is quantity, also known as mole, the volume of gas, the temperature, and also the pressure. So, what is meant by pressure of gas? So, actually, when gas a light with the wall of container, it will exert pressure onto the wall of container. So this is what we call as gas pressure. So the SI unit for gas pressure is Pascal, which is equal to 1 nm negative 2. So 1 atm is equal to 760 millimole mercury or 760 torr, and it is also equal to 101325 Pascal and also equals to 101325 nm negative 2. So you should know how to convert the pressure into SI unit. If we have 750 millimole mercury, how do we convert into atm? So let's look at this together. So 760 millimole mercury is equal to 1 atm. So if we have 740 millimole mercury, so how do you want to solve this type of question? So mathematically, you will divide 740 with 760 times 1. Then you will get the answer. So the answer here is 0.9737 atm. Now let's look at example 2. If we have 100,000 nm negative 2, then how do you convert this into atm? So from the constant value, we know that 101,325 nm negative 2 is equal to 1 atm. So if we have 100,000, so just divide 100,000 with 101,325 and times 1. Then you will get the answer in atm. The answer is 0.9869 atm. So that's all for part 1.
Hi, don't forget to like and subscribe this channel.
Now we will continue with the second part of lecture 1. So for the learning outcome in this video, you should be able to define gas law, which is Boyle's law and Charles' law. Then you should be able to sketch and interpret the graph of Boyle's and Charles' law. So Boyle's law states that at constant temperature, the volume of a fixed amount of gas is inversely proportional to the gas pressure, meaning that when the volume of container decreases, therefore the pressure will increase. So the same goes to the other way around.
When the volume of the container decreases, the pressure of the gas inside the container will increase.
So now let's look at this diagram here. When we pull up the piston here, the volume of container will increase. Therefore, the pressure will decrease. And the second diagram shows that the piston is pushed downward. Therefore, the volume of container decrease. Therefore, the pressure of gas in this container will increase. So mathematically, volume is inversely proportional to pressure. Therefore, it is directly proportional to 1 over P at constant temperature and number of moles. So P times V equals to K, which is constant. And for a system that changes pressure and volume, the equation is given as below. P1 times V1 equals to P2 times V2, where P1 and V1 is the initial pressure and volume, while P2 and V2 is the final pressure and volume. This is the graph to show the relationship between pressure and volume. So P is the y-axis and volume is the x-axis. So we can see in this graph that pressure and volume is inversely proportional. If we plot P against 1 over V, it will obtain a positive gradient. It means that pressure is directly proportional to 1 over V. If we plot volume against 1 over P, we will also obtain a positive gradient. So it means that volume is directly proportional to 1 over P. But if we plot P times V against P, we will get a horizontal line, meaning that P times V is constant. Now let's look at example 1. This is actually simple calculation for Boyle's law. A sample of oxygen gas occupies a volume of 2.0 liter at a pressure of 180 m. Calculate the pressure of the gas if the volume is then increased to 5 liter at a constant temperature. So the information given in this question is P1, where the value is 180 m, V1 is 2 liter, V2 is unknown, and V2 given is 5 liter. So we just have to use the relationship P1 times V1 equals to P2 times V2. Then just substitute all the values given into the formula. So we will get P2 equals 2.5 atm. So in this example, the initial volume is 2 liter and the pressure is 180 m. But if we increase the volume to 5 liter, the pressure will increase to 2.5 atm. Now we'll continue with Charles' law. So Charles observed that at constant pressure, the volume of a gas expands when heated and contracts when cooled. When the hot air balloon is flying high up in the sky, the gas inside the balloon is actually heated using the flame. But if the balloon is going to land down, the air inside the balloon is cooled down so that the volume of the gas inside the balloon will decrease. So at constant pressure, the volume of a fixed amount of gas is directly proportional to the absolute temperature of the gas. So V is directly proportional to temperature at constant pressure and number of mole. Therefore, volume is equal to K, which is constant, times temperature. Or we can rearrange this relationship, V over T equals to K, where K is the constant. For a system that changes temperature and volume, the relationship is given as below. V1 over T1 equals to V2 over T2. V1 and T1 is the initial volume and temperature, while V2 and T2 is the final volume and temperature. So keep in mind, to use this formula, you have to ensure that temperature is in unit Kelvin. So to convert temperature from degrees Celsius into Kelvin, we just have to add the temperature given in degrees Celsius by adding 273.15. So if we plot volume against temperature, we will obtain a straight line graph with positive gradient, but the x-intercept will be slightly on the left, which is on negative 273.15. But if we plot volume against temperature in Kelvin, we will have intercept at 0. Now let's look at example 2. A sample of carbon monoxide gas occupies a volume of 3.2 liter at 125 degrees Celsius. The sample is then cooled at constant pressure until it contracts to 1.45 liter. We have to calculate the final temperature in degrees Celsius. So V1 in this question is 3.2 liter. P1 is 1 to 5 degrees Celsius So we have to convert into Kelvin before we insert into the formula. So you will get V2 given is 1.54 liter, and we have to calculate the final temperature in unit degree Celsius. So just insert into the formula V1 over T1 equals to V2 over T2. So 3.20 over 398.15 equals to 1.54 over T2. So we will get 191.61 Kelvin. So to convert into degree Celsius, just subtract with 273.15. So you will get negative 81.54 degrees Celsius. The combination of Ross law and Shell's law is given as below. We know that volume is directly proportional to 1 over P, and volume is directly proportional to temperature. So if we combine both of these relationships and volume is the subject, so we will get volume is directly proportional to T over P. Now, rearrange this formula. So, we replace this sign with equals to and put a constant. So, you will get V equals to K T over P. Now, rearrange this formula. So, we will get PV over T equals to K. So, for a system that changes in pressure, volume and temperature, the relationship is given as below. P1 times V1 over T1 equals to P2 times V2 over T2. Now let's look at this example. So a sample of methane gas occupies 25.5 liter at 298.15 Kelvin, and the pressure given is 153.3 kilopascal. Then we have to find the volume at STP. Now let's list down all the information given. So V1 given in the question is 25.5 liter. The initial temperature is 298.15 Kelvin, and the initial pressure is 153.3 kilopascal. So at STP, it means that standard temperature and pressure, the temperature is 0 degrees Celsius and the pressure is 1 atm. So you have to convert the temperature into Kelvin, and since we have pressure in different units, P1 is given in kilopascal and P2 is in atm, so you have to convert one of them into the same unit. So let's convert the initial pressure into atm. To convert into atm, just divide the pressure given in kilopascal by 101.325. Then you will get the answer in atm. So you will get 1.513 atm. So 0 degrees Celsius is equal to 273.15 Kelvin. So after all the conversion unit, we can insert the values into the formula. P1 times V1 over T1 equals to P2 times V2 over T2. Just substitute all the values given into the formula. P1 is 1.513, V1 is 25.5, T1 is 298.15, V2 is 1 atm, V2 is unknown, and T2 is 273.15. So finally, you will get the answer for V2. So you will get the answer 35.35 liter.
Hi, don't forget to like and subscribe this channel.
We will continue with the third part of lecture 1. So for the learning outcome for this video, you should be able to define gas law, which is Avogadro's law, and define Dalton's law. Avogadro's law states that at constant temperature and pressure, the volume of a gas is directly proportional to the number of moles of the gas. So let's say we have a container here where the volume is 22.4 liter and the pressure is 1 atm, and we have 1 mole of gas inside this container. If we add gas into this container, from 1 mole it becomes 2 mole. The volume of the gas inside this container will also increase. And if we remove the gas from this container from 2 mole to become 1 mole, the volume of the gas inside the container will decrease. So mathematically, volume is directly proportional to the number of mole of gas at constant temperature and pressure. So this relationship will give rise to V equals to K times N, where K is a constant. And if we rearrange this equation, we have V over N equals to K. And for a system that changes number of mole and volume, the equation is given as below. V1 over N1 equals to V2 over N2. Now let's look at this example. The moles of chlorine gas kept in a cylinder with piston occupies a volume of 49 liter. When another 3 moles of chlorine gas is pumped into the cylinder at constant temperature and pressure, the piston moves upwards to accommodate the gas. Calculate the final volume of the gas. So in this question, we have the initial number of mole, which is 2 mole, and the initial volume of the container, which is 49 liter. And then the final number of mole is 3 plus 2, because we have 2 moles initially, then we add another 3 mole. Therefore, the total number of mole here is 5. And we have to find the final volume of the gas. So by using the relationship V1 over N1 equals to V2 over N2, just substitute all the values into the formula. 49 over 2 equals to V2 over 5. And finally, we can calculate the value of V2. So we will get 122 liter. Next, we go to Dalton's law. So Dalton's law of partial pressure states that the total pressure of a mixture of non-reacting gases is the sum of the partial pressures exerted by each gas in the mixture. So let's say we have mixture of 2 gases, which is gas A and gas B. So the total pressure for the gas is pressure of gas A plus the pressure of gas B. Now let's look at this diagram for better explanation. So let's say we have 3 types of gas here. We have gas A, where the pressure is 1 atm, gas B, and the pressure is 2 atm, and gas C, the pressure is 0.5 atm. So assuming that gas A gas B and gas C does not react with each other, and they all put in the same container. So in this container, we have mixture of gas A, B and C. If you have to calculate the total pressure, we just have to sum up the pressure of each gas individually. So 1 atm plus 2 atm plus 0.5 atm. So the total pressure inside this container is 3.5 atm.
Hi, don't forget to like and subscribe this channel.
Now we will continue with the first part of lecture 2. So for the learning outcome, you should be able to explain the ideal or non-ideal behaviors of gases in terms of intermolecular forces and molecular volume. And you should be able to explain the conditions at which real gas approach the ideal behavior. So this is the comparison between ideal gas and real gas, which is also known as non-ideal gas. So for ideal gas, so we all know that between particles, there is actually intermolecular force between each of them. But for ideal gas, we will ignore the intermolecular forces that exist between each gas particle. And gaseous molecules are very small and they have negligible volume. So we assume that the volume of gas is actually the volume of container. We don't take into account the volume of the gas particle. So we will just make assumption that if we have 1 liter of container, so we will also have 1 liter of gas. So now let's go to real gas. For real gas, we take into account the intermolecular forces that exist between each gas particle. Therefore, the intermolecular force is significant or important because we consider the intermolecular force for the gas particles. And the gas molecules have a certain volume. Therefore, the volume of gas is not the volume of container for real gas. So how real gas will deviate from ideal behavior? So deviations from ideal behavior are more significant at high pressure and low temperature. It means that ideal gas can be real gas at these two conditions, which is high pressure and low temperature, because these two conditions will affect the intermolecular forces between the gas particles. And how is that? At high pressure, the volume of gas decreases, as we can see in this animation. So when the volume of gas decreases, the gas molecules here become closer to one another. So when they are closer to one another, therefore, the intermolecular force is important. So we cannot ignore the intermolecular force when the gas particles are close to each other. Therefore, the ideal gas
is now become real gas.
Now let's look at the second condition, which is low temperature. So how can low temperature make ideal gas become real gas? So according to the kinetic molecular theory, temperature is directly proportional to the kinetic energy. So at low temperature, gas molecules possess very low kinetic energy. So the gas particle will move very slowly. So the kinetic energy of gas molecules can no longer overcome the intermolecular force. We cannot ignore the intermolecular force when the kinetic energy is very low. Therefore, the intermolecular force now becomes significant. we cannot ignore the intermolecular force. Therefore, ideal gas will become real gas. So how do gas approach ideal behavior? So all gases show ideal behavior at low pressure and high temperature. And why is that? So at low pressure, the volume of container increase. So the gas molecules are far apart from each other. Therefore, the intermolecular force can be neglected when the gas molecules are far from each other. Therefore, real gas will behave ideally.
At high temperature, since the kinetic energy is directly proportional to temperature, therefore, gas molecules will possess high kinetic energy. The kinetic energy of gas molecules can overcome the intermolecular forces, and therefore, the intermolecular forces cannot be ignored.
And therefore, real gas will behave ideally. So this is ideal gas equation, PV equals to nRT. And this is van der Waals equation, which is applied for real gas. So as we can see here, for ideal gas equation, the pressure is P, but for van der Waals equation, where IMF or intermolecular force becomes significant, the pressure is now P plus N squared A over V squared. While the volume in ideal gas is V, but for real gas, the volume is V minus NB. So the ideal gas equation is redesigned to describe the real gas behavior more accurately. So the van der Waals equation given here is actually correcting two parameters of gas, which is pressure, since we take into account the attractive forces between gas molecules, and the volume, since we take into account the volume of gas molecules. So the intermolecular forces between molecules for ideal gas is negligible since the molecules are far apart from each other. Therefore, the pressure in ideal gas will be greater because we ignore the IMF. But for real gas, since we take into account the intermolecular force, therefore the pressure exerted by the gas molecules onto the wall of container will be lower. So the pressure for real gas is lower compared to ideal gas. So P real is smaller than P ideal. So this is actually corrected by adding coefficient n squared A over V squared. So the pressure in ideal gas is equal to pressure of real gas plus n squared A over V squared. So n squared A over V squared is the corrections for molecular attractions intermolecular forces. So A is constant that indicates the strength of intermolecular force between gas molecules. So the higher the value of A, the stronger the intermolecular force for the gas. And the unit for A is atm, L squared mol negative 2. Now let's go to the volume of gas. So this is the volume of ideal gas, where the volume of gas is equal to the volume of container since we neglect the volume of each gas molecule. But for real gas, we consider the volume of the gas particle. So the gas molecule have certain volume. Therefore, the volume of real gas equals to the volume of container plus the volume of gas. Since volume of ideal gas is smaller than the volume of real gas, Therefore, the term volume needs to be deducted by coefficient NB. So V ideal equals to volume of real gas minus N times B. So what is NB? So NB is the correction for volume of molecules since we take into account the volume of gas particle in real gas. So N is the number of moles of gas, while B is constant that indicates the actual volume occupied by the gas molecules. So the greater the value of B, the larger the molecules or atoms for the gas. And this is the unit for B.
Hi, don't forget to like and subscribe this channel.
Now we will continue with the second part of lecture 2. So we will study a new subtopic for this part, which is liquid. So in this subtopic, you should be able to relate the properties of liquid to intermolecular forces, molecular arrangement, molecular motion in explaining shape, volume, surface tension, viscosity, compressibility, and diffusion. So there are few factors which affect the general properties of liquid, and they are arrangement of particles and intermolecular force. So for arrangement of particles, the liquid state is an intermediate between the solid and gaseous state. And in a liquid, the particles are very closely packed as compared to the gaseous state. While the intermolecular force is the strength of the intermolecular forces between molecules. So the intermolecular force for solid is stronger compared to liquid, and the intermolecular force for liquid is stronger than gas. So the types of forces between molecules in liquids are van der Waals forces and hydrogen bonds. So if we compare between the three states of matter, so let's look at the first one, which is molecular arrangement. So for solid, the molecules are very close together and neatly arranged. And for liquid, the molecules are still close together, but not neatly arranged. It means that the arrangement of particles can be changed. While gas, the molecules are far apart from each other. For intermolecular force, for solid it is the strongest, for liquid weaker than solid, but gas is weakest, which is almost none. For molecular motion, in a solid, molecules can vibrate but do not move from their position. For liquid, molecules are able to move around. But for gas, molecules are moved about very fast in all directions, meaning that they are free to move around. Now let's look at the general properties of liquids. So liquids have definite volume, meaning that the intermolecular force is strong enough to keep the liquid molecules together. And it has indefinite shape, meaning that the intermolecular force is not strong enough to hold the molecules in a fixed position. It means that it can change the shape according to the volume of container. Now let's look at surface tension. So surface tension is the amount of energy required to stretch the surface of a liquid by a unit area. So if we look at this diagram here, if we have an object on a surface of a liquid, so the liquid molecules will stretch the surface in all directions on the surface. So liquid molecules at surface are pulled downward and sideways from the neighboring molecules, but not upward away from the surface. It is different from an object inside the liquid. So let's look at this paper clip here. Why can it float on top of a liquid? So actually this is what we call as surface tension. The surface tension of liquid keep the plate to float on the liquid. So the intermolecular force will pull the surface molecules into the liquid, and it causes the surface to stretch and tighten. The stronger the intermolecular force, the higher the surface tension. Now let's look at viscosity. Viscosity is resistance of liquid to flow. The greater the liquid's viscosity, the more slowly it flows. So now let's look at honey. So it has high viscosity. So it means it is very hard to flow compared to liquid with low viscosity such as water, juice and oil. So viscosity is depending on the intermolecular force between the molecules. The stronger the intermolecular force, therefore the higher the viscosity, the harder it is to flow. And the last one is compressibility. Can we compress liquid? So actually there is very little empty space between liquid molecules because the molecules are close to each other. So let's say we have a string here and we close the end of the string and we insert liquid into the string. So actually we cannot push the piston anymore because of the empty space in the liquid, which is very small. So liquid has low compressibility. And the last one is diffusion. So liquid can easily diffuse and mix with other liquid. So diffusion rate of a liquid is low because liquid molecules are close to each other, has lower kinetic energy than gases, and the stronger intermolecular force slow their movement. So let's say we drop an ink into the glass of water. Therefore, the ink can actually diffuse into the water, but it takes quite a time for it to diffuse completely into the glass of water.
Hi, don't forget to like and subscribe this channel.
Now we will continue with the third part of lecture 2, which is still liquids. So for the learning outcome for this video, students should be able to explain vaporization and condensation process based on kinetic molecular theory and intermolecular forces. The vaporization process occurs at the surface liquid molecules, which has higher kinetic energy than inner molecules because it is surrounded by less number of molecules. It can occur at any temperature below boiling point when the surface liquid molecules gain enough kinetic energy to overcome the intermolecular force. The liquid molecule will leave the surface as vapor or gas. Now let's look at this diagram here. So let's say we have a beaker of liquid. Then the liquid molecule at the surface possess enough kinetic energy. Therefore, it will overcome the intermolecular force between the liquid molecules, and therefore it will escape as gas. So there are three factors that affect the vaporization rate, which is surface, temperature, and intermolecular force. For surface area, the larger the surface area, the higher the chances for the molecules to escape from the surface. Therefore, vaporization rate will increase. So let's say we have a plate of water and a jar of water. So which one do you think will vaporize faster? So of course, the plate of water will vaporize faster since it has larger surface area. Now let's go to temperature. So we know the relationship between temperature and kinetic energy is directly proportional. Therefore, when the temperature increases, more molecules have enough energy to escape from the surface of the liquid. Therefore, vaporization rate increases. So if we compare between 0 degrees Celsius and 60 degrees Celsius, so the vaporization rate at 60 degrees Celsius will be higher. And the last one is intermolecular force. So the weaker the intermolecular force of the liquid molecule, the faster the vaporization rate. So water has stronger intermolecular force compared to alcohol. Therefore, water vaporizes very slowly compared to alcohol. Now let's look at this animation. For vaporization process, so the liquid molecules at the surface of liquid possess enough kinetic energy from the surrounding. Therefore, it will overcome the intermolecular force between the liquid molecules and it escapes the liquid surface as gas. Now let's go to condensation process. So condensation process occurs when temperature is lowered and the kinetic energy of vapor molecules decrease. So vapor molecules become close to each other and form stronger intermolecular force. The kinetic energy of the vapor molecules can no longer overcome the intermolecular force, therefore will turn to liquid. Now let's look at this animation. So we have gas molecules above the liquid surface. So when the temperature of the surrounding is lowered, so the kinetic energy of the gas molecules cannot overcome the intermolecular force between each of the gas molecules. So what happens here? It will be trapped to the surface of liquid and it will turn back into and vapor will form liquid.
Hi, don't forget to like and subscribe this channel.
Now let's continue with the first part of lecture 3. For the learning outcome in this video, you should be able to explain the fixed shape of a solid, then apply the kinetic concepts to explain the following process, which are freezing, melting, sublimation and deposition. So now let's look at the properties of solid. So solid has fixed shape because it has strong intermolecular forces between the molecules. The molecules are arranged closely together and the particles can only vibrate and rotate about fixed position. Solid, liquid and gas are interconvertible, meaning that they can convert into one another through different processes. We have liquid, solid and gas. Solid turns into liquid through melting and liquid turns into solid through freezing. Solid turns into gas through sublimation and gas turns into solid through deposition. Liquid turns into gas through vaporization and boiling, while gas turns into liquid through condensation. Let's look at the first process, which is freezing. Freezing is a process when liquid turns into solid. When the temperature of liquid is lowered, the kinetic energy of the liquid molecules will decrease Therefore, the kinetic energy of the liquid particles cannot overcome the intermolecular forces between the molecules. Then, the intermolecular forces are strong enough to hold the molecules in fixed position. Therefore, the liquid molecules turn into solid. Now let's look at the next process, which is melting. Melting is a process when solid turns into liquid. When the temperature of solid increases, the kinetic energy of solid molecules will also increase. The molecules has enough kinetic energy to overcome the intermolecular forces between the molecules. Therefore, the solid molecules turn into liquid. Next, let's look at sublimation process. Sublimation process is a process when substance goes directly from solid to gaseous state without passing through the liquid state. What happens here? The temperature of solid increases. Therefore, the kinetic energy of the solid molecules increase. The molecules has enough kinetic energy to overcome the intermolecular forces between the molecules. Therefore, the solid molecules turn into gas. This is an example of sublimation process when solid carbon dioxide turns into gas. The last one is deposition process. So this is a process when gas turns into solid state without passing through the liquid state. This is the opposite process of sublimation. When the temperature of a gas is lowered, the kinetic energy of the gas molecules will decrease. So the kinetic energy cannot overcome the intermolecular forces between the molecules. The intermolecular forces are strong enough to hold the molecules in fixed position. Therefore, the gas molecules turn into solid. An example of deposition process is the formation of snow. End of part 1.
Hi, don't forget to like and subscribe this channel.
Now let's continue the second part of lecture 3. For the learning outcome in this video, students should be able to differentiate between amorphous and crystalline solids, then state the following types of crystalline solids with appropriate examples. Number 1, metallic. Number 2, ionic. Number 3, molecular covalent. And number 4, giant covalent. Now let's look at types of solid. There are two types of solid, which are crystalline solid and amorphous solid. So there are few differences between these type of solids. The first one is in terms of the arrangement. For crystalline solid, the atoms, ions or molecules are ordered in well-defined arrangement. Or in other words, the T-structure is extended in all directions. While for amorphous solid, the atoms, ions or molecules have no orderly structure, or the arrangement of the atoms are random. Next, let's look at the formation of this solid. For crystalline solid, it is formed when a saturated liquid is cooled slowly, while amorphous solid is formed when the saturated liquid is cooled rapidly. The next one, when crystalline solid is cut, they split perfectly into even size. But for amorphous solid, when they are cut, they break into uneven pieces. The next one, For crystalline solid, its atom, molecules or ions occupy specific position, but amorphous solid, its atoms, molecules or ions occupy random position. Examples of crystalline solids are snowflakes, sugar, and table salt, while examples for amorphous solid, glass, plastic material, and charcoal. So the conclusion here, both amorphous and crystalline solids may look alike in terms of appearance, but they are different from each other in terms of their physical properties. Now let's look at types of crystalline solid. There are 4 types of crystalline solid. The first one is metallic solid, ionic solid, molecular covalent solid, and giant covalent solid. Now let's look at metallic solid. So metallic solid is closely packed structure and composed of positively metal ions immersed in the sea of delocalized electrons attracted to each other by metallic bond. So all metallic elements are metallic solid. For example, elements from group 1, group 2, and also transition metals. This is an example of sea of delocalized electron for sodium. Positively sodium ions, which is immersed in the sea of electron of sodium. Now let's look at ionic solid. Ionic solid consists of ions, cation and anion, which are held together by ionic bonds. An example of ionic solid is sodium chloride, which is also known as table salt in the kitchen. In NaCl, there is lattice structure of Na plus and Cl minus, which is attached to one another by strong ionic bonds. So all salt which consists of ionic bond is also known as ionic solid. Now let's look at molecular covalent solid. Molecular covalent solid is composed of molecules held together by intermolecular forces, which is van der Waals forces or hydrogen bonds. Let's look at the example. Please change the example given in your notes to glucose, ice, and sulfur because the examples given in your lecture note is incorrect. Oxygen is in the form of gas, so it is not solid. Water is liquid, and ammonia is gas, so we cannot consider them as solid. Please change all these examples. So now let's look at this molecule here. This is H2O. So when H2O converts into solid, it is also known as ice. So between each H2O molecules, there is strong hydrogen bond. So all solid molecules which are held together by van der Waals forces or hydrogen bonds, therefore they are known as molecular covalent solid. Now let's look at giant covalent solid. Giant covalent solid is very large molecule. It is composed of atoms which are linked together by strong covalent bonds. Examples of giant covalent solid are diamond, graphite, and silicon oxide. Each carbon atom in diamond is tetrahedrally bonded to one another by strong covalent bond. The same goes to graphite and also silicon dioxide. But for graphite, between each layer of carbon, there is weak van der Waals forces. This is the structure of diamond. each carbon atom is bonded to another carbon atom by strong covalent bond. While the structure of graphite, there is strong covalent bond between each carbon atom, but between each layer there is weak van der Waals forces that hold the layers together. This diagram shows the ionic bond in NaCl, while the diagram below here shows the sea of delocalized electron in metals. This diagram here shows formation of strong covalent bond between each carbon atom, while the diagram below here shows the formation of hydrogen bond between each H2O molecules. Now let's look at the comparison between gas, liquid and solid. The first one is the shape and volume. For gas and liquid, since the particles can move past one another, therefore the shape and volume will follow the shape of container. But solid retains a fixed volume and shape since they have rigid particles that lock into place. In terms of compressibility, gas is highly compressible, while liquid is harder to compress, and solid is very hard to compress since there is very little space between the particles. The last one, in terms of flow, gas and liquid can flow easily since the particles can move past one another, but solid does not flow because the particles do not move past one another.
Hi, don't forget to like and subscribe this channel.
Now let's continue with the third part of lecture 3. In this part, you are going to learn a new subtopic which is phase diagram. For the learning outcome in this video, you should be able to define phase, triple point and critical point. Next, identify triple and critical points on the phase diagram. Then, sketch the phase diagram of water and carbon dioxide. First, let's learn what is meant by phase. Of a system are parts of it which are separated by a distinct boundary. It means that we can see clearly the boundary between each phase, such as between solid and liquid and gas. Let's look at example. If we have a mixture of ice and water, therefore we have two-phase system where we have solid phase which is ice and the liquid phase which is water. Now let's look at this example. We have a beaker of salt and water where some of the water evaporate off on top of the liquid surface. So in the bottom of the beaker we have salt. In the middle of the beaker we have salt and water. And on top of the liquid we have water vapor. So there are three phases in this beaker. Therefore, this is a three-phase system. Now let's look at this example. For the first one here, we have water and food coloring, where both liquid are miscible with each other. Therefore, this is one-phase system where both substance in this beaker is in the form of liquid. But the second one here, both are liquid, but the liquid are not miscible among each other because we have oil and water. Therefore, this is a two-phase system. Heterogeneous means that the liquid is not miscible with each other. Now let's look at this example. This is one phase system where we have a mixture of gas in this container. And this one here, we have one phase. Gas in the container are miscible with each other. Now let's look at another example. For a mixture of gas, there is only one phase because these gases are well mixed and we cannot see the boundary between the gases. For two liquids, where both liquids do not mix, for example, oil and water, therefore this is a two-phase system because we can see clearly the boundary between the two liquids. But for two liquids, which is well mixed with each other, for example, alcohol and water, this is only one-phase system because we cannot see the boundary of the solution. So as a conclusion here, for liquids that are heterogeneous, therefore, we have two-phase system, but for liquid that is homogeneous, there is only one phase. Now let's look at this example. Identify the phases of the following under normal conditions. The first one is steel, number 2 mercury, number 3 aqueous ethanol, and number 4 a saturated solution of copper sulfate stored in a closed bottle. For the first one, steel is metal, therefore the phase is solid. The second one, mercury. Mercury is metal but it is in the form of liquid. For aqueous ethanol, it is in the form of liquid. And the last one, the phases are solid, liquid and gas. Solid copper sulfate is in equilibrium with aqueous copper sulfate and water vapor. Now let's look at triple point and critical point. Triple point is the temperature and pressure at which the three phases, which is gas, liquid and solid, are in equilibrium. Quadruple point is the point at which there is no boundary between the liquid phase and the gas phase. Now let's look at this phase diagram for better explanation. On the y-axis, we have pressure, and on the x-axis, we have temperature. There are three phases in this phase diagram, which is solid, liquid, and vapor. On the left-hand upper side of the phase diagram, substance have tendency to become solid. This is because at high pressure and low temperature, the arrangement of particles of substance are close to one another. Therefore, they have tendency to become solid. Next, as we go towards the right, meaning that we increase the temperature, substance have tendency to become liquid. Because as we increase the temperature of solid, it will melt and become liquid. The arrangement of particles in this part here is further compared to solid. So we have line AC, TB, and TC. Line AT separates phase between solid and vapor. Line TB separates the phase between solid and liquid, while line TC separates the phase between liquid and vapor, meaning that along line AT, this is the sublimation point of the substance. Line TB is the melting point of the substance, while line TC is the boiling point of a substance. Now let's look at vapor. On the lower part of the phase diagram, substances have tendency to become vapor because at low pressure and high temperature, the arrangement of particles of any substance will be further from one another. Therefore, they have tendency to become vapor. This is the three regions of a single phase. So, region ATB is the solid phase, region BTC is the liquid phase, and region ATC is the gas phase. Line TC is the boiling point at certain temperature and pressure. Line TB is the variation of melting point at different temperature and pressure, while line TA is the variation of sublimation point at different temperature and pressure. Now let's look at phase diagram of carbon dioxide. At 1 atm, if we read the phase diagram towards the right, firstly, carbon dioxide is in the form of solid. But as the temperature increases and reaches 195 Kelvin, carbon dioxide will turn into vapor since line AT is the sublimation point of carbon dioxide. So this is the point where carbon dioxide solid turns into carbon dioxide gas. At higher pressure, which is 5.2 atm, carbon dioxide firstly will exist as solid. But if we increase the temperature towards the right and reaches point T, so this is what we call as triple point, meaning that at this temperature and pressure, carbon dioxide will exist as solid, liquid, and gas at the same time and are in equilibrium. Now let's look at the last one. When we increase the pressure to 72.9 atm, at low temperature, carbon dioxide is still a form of solid. But if we increase the temperature and it reaches this point here, so this is the point where carbon dioxide solid will turn into carbon dioxide liquid. And then as we increase the temperature, carbon dioxide will exist as liquid. And finally, at 304 Kelvin, it reaches point C. This is called as the critical point where there is no boundary between liquid and vapor state. Now let's look at the phase diagram of H2O. At 1 atm, firstly, H2O exists as solid, which is ice. If we increase the temperature to 273.15 Kelvin, ice will turn into liquid. So this is the point where ice starts to melt. Next, if we increase the temperature furthermore towards the right, this is the point where H2O in the form of liquid will turn into H2O in the form of vapor. So this is called as the boiling point of water at 1 atm. Now let's look at the triple point of water. So triple point of water exists below 1 atm. So this is the point where H2O exists as solid, liquid, and vapor in equilibrium. The difference between phase diagram of CO2 and water is the line TB, where we have negative gradient for water. This indicates that ice is less dense than water. This also means that water is easier to melt at higher pressure. And this is why the melting point of water lies towards the left.